Video is going to focus on distance, rate, time, word problems. So just to recap and review, this is the basic formula that we're using. Distance equaling rate times time, D for distance, R for rate, T for time. The formula works on objects that are in uniform motion, which means they move without changing speed or rate. And one thing to note in this video, because we have a problem that this pertains to, the rates that were quoted are given miles per hour or kilometers per hour. If you are given half an hour, a third of an hour, a tenth of an hour, remember that 1 hour is 60 minutes. So if you're quoted a half an hour or a portion of an hour, it would be a fractional portion out of 60. And we'll see that in one of the word problems coming up first. There are 3 problem types: objects traveling in opposite directions, which was in a previous video. The focus of this video is going to be objects traveling in the same direction, and then the third video will discuss objects making a round trip, or a single object making a round trip. So this video's focus is objects traveling in the same direction. So let's first look at what that means. If you have objects traveling in the same direction, that means that you've got one object that would be, let's see, I'm trying to find a piece of paper to write on. And let's see, I'll just use this. This is as good as anything. Objects traveling in the same direction. You have one object that leaves, traveling, let's say traveling eastbound. And then you have a second object that leaves later, traveling in the same direction, covering the same distance. But I like to think of this as fast and slow. One object, or one car, one plane, one person leaves first, traveling at a slower rate. Then a second object leaves later, traveling at a faster rate. So these problems are always asking, when does the second object that's traveling faster, when does the second object catch up with the first object? So that's the basic premise of a same direction problem. And looking at the notes for learning to continue completing these, with the opposite direction problems, the rate time of one object plus the rate time of the other object equals the total distance covered. Well, in this particular problem set, or this particular problem type, since both objects are traveling in the same direction, they're covering the same amount of territory. They're just covering that distance at different rates. And within a different time frame. So the ratio, or the equation set up for 2 objects traveling in the same direction, it's the rate time of one object is set equal to the rate time of the other object. So instead of adding the 2 together, you take the 2 expressions and set them equal to each other. So let's see what that looks like in the problem that's given in the learning notes, same direction. So this is the problem that's given in the learning notes for same direction. And I'll get a smaller pen to do this. So here I have 2 airplanes. I have a small airplane. Once again, I'm going to use my chart. And, one row for one object, the second row for the second object. Columns are rate, time, and distance. Distance is the product of the rate and the time of a single object. So here I have a small plane and a large plane. So I'm going to go ahead and label my rows small and large. A small plane leaves the airport flying north at 240 miles per hour. So the rate is straight up given. A larger plane leaves 30 minutes later, following the same flight plan, flying at a rate of 360 miles per hour. So in this particular problem, small plane, large plane, one traveling slower than the other. So I'm straight up given the rates. What I'm not given are the times. So that's what I have to figure out. I need to figure out what my times are. If the small plane leaves, and I will let the variable t represent the time for the small plane, the larger plane leaves 30 minutes later. So this is the key phrase right here, 30 minutes later. So I'm going to label his time as the time that the small plane's in the air minus 1/2. And I'll go with 1/2 because 1/2 would be 30 minutes out of an hour would be 1/2 of an hour. And then the distance covered by the small plane will be 240 t, and the distance covered by the large plane, t minus 1, 360 times t minus 1/2. Rate time of one times rate time of the other. They're covering the same distance. They're just doing it at different rates and in different amounts of time. So I'm going to take the 2 expressions in my final column and set those 2 expressions equal to each other. So the rate time of slow equaling the rate time of fast And since they're both covering the same distance, that allows me to set those two expressions equal to each other. Now solving this, and then t is going to be positive 180 over 120. This is time in per hours, miles per hour. So if I remove the common 60 to both of these, that leaves me with the fraction 3 over 2. To interpret that to time, that's 1.5 hours. So that means that, and I'll switch ink colors, that means that the small plane is in the air for 1.5 hours. And then the large plane is only going to be in the air for 1 hour. So I've got two objects traveling in the same direction at different rates. One object is traveling slow, one's traveling faster, and the premise of these problems is always the same. When does the faster object catch up with the slower object? Faster object is traveling less time, smaller object is traveling more time. When do they meet? When do they catch up? And here with this particular problem, you also have to be comfortable with the time component, the fractional portion of 60 minutes. So I'm now going to switch to the CUDA problem set. So I've generated an entire problem set for same direction problem practice. This is in topics labeled same direction. So I'm going to do 4 problems on this from this particular problem set in order to give you all confidence and practice with this skill. So I'm going to start with number 1 in the CUDA set, and you can access the problems and read along as I go, and I'll move to a larger sheet of paper. So this is my same direction scenario. My basic setup is rate time equaling rate time, and I'm doing number 1. So in number 1, I have a passenger train and a freight train. So I've got my rows labeled passenger train and freight train. And let me look at my notes as I'm doing this. All right, so the passenger train, let's see, I'm straight up told that the passenger train is traveling at a rate of 50 miles per hour. So the passenger train is traveling at 50 miles per hour, and the freight train is traveling at 60 miles per hour. So their rates are straight up given. What I'm not given in this particular problem are the times, so that's what I need to pay really close attention to. So here, the passenger train leaves traveling west at 50 miles per hour. A freight train left 2 hours later and traveled in the same direction but with an average speed of 60. How long did the passenger train travel before the freight train caught up with it? So you can see that this is the basic problem type for these for this same direction scenario. So here, if I let the freight train be the variable t, the freight train left 2 hours later. So that's going to imply that the passenger train has already been traveling for 2 hours before the freight train leaves. So the passenger train's time is going to be t plus 2. That's if I choose to let the freight train be t, the passenger train's traveling for 2 hours longer than the freight train. I would also have the option to do, let me get a different ink color. I'm going to solve mine like this, but if I wanted to, I could let this be t, and then this would be t minus 2. So you just need to decide what works for you, which one you prefer. So with these, I'm going to now set these two expressions equal to each other. And I'll just go with what I've set up. Setting these two equal to each other. And then 100 equaling 10t, therefore t is 10. So going with the orange setup, that means that the freight train is traveling for 10 hours, and the passenger train will be traveling for 12 hours. So just make sure that you understand that component of how to represent the time. Had I chosen to go with the pink, then my variable value would have been 12. I would have subtracted 2 to get 10. You would get the same answer both times. And the only way to know what you really prefer is to do the problems and see which method always works for you. I'm now going to move on and do number 4. And let me get the wording for number 4. So number 4 is, okay, so trains And here I have a diesel train. This is problem number 4. I have a diesel train traveling toward Johannesburg at an average speed of 10 miles per hour. So I've got my chart set up with the diesel train, and then the other type of train in this problem is a cattle train. So the diesel train is traveling at a rate of 10 miles per hour. So I'm going to go ahead and label my rate column. And then the cattle train is traveling at 65 miles per hour. So I'm going to go ahead and label that 65 miles per hour. And now the time component for this particular problem. The cattle train left, let's see, what does it say? Okay, the cattle train left sometime later, traveling in the same direction. After traveling for 2 hours, the cattle train caught up with the diesel train. So the cattle train is traveling for 2 hours. And the diesel train is traveling for the same 2 hours, but the diesel train has also been traveling for an unknown amount of time prior to the departure of the cattle train. So what I'm going to do with this is take the two expressions, multiply the two expressions together, set them equal to each other. So the rate time of the diesel train equaling the rate time of the cattle train. And in this particular problem, I'm going to end up with this. And let's see, I'm looking at my support work, and T is 11. So that means that the diesel train is traveling for 13 hours before the cattle train catches up with it. So just to go back and recap the same direction problems, one object, they're covering the same amount of time, but one object is traveling slower and traveling for much longer. The second object is traveling at a much faster rate and for less time. So this problem really does exemplify and show that. Let's move on now, and I have chosen to do number 7 on the video. So here's my support work, or here's my framework for number 7, and then the problem itself. So I've also arranged this CUDA problem set like the other. 1 through 6, you are given rate, you find time, and then the next 6 problems, you're given the times and you're to find the rate. So in number 7, I'm going to be finding the rate. So here I have Nicole and John. And let's see, Nicole. Okay, here we go, Nicole and John. All right, so Nicole left school and drove toward the desert. John left 1 hour later, driving 12 kilometers faster. So here we go, that's something I can work with. He is driving 12 kilometers faster. So if I let her be R, his rate is R plus 12. And then I need to go back and read the timing piece carefully. He leaves 1 hour later. So that implies that she's already been traveling for an hour. And in an effort to catch up with her, after 4 hours, he finally catches up with her. So he's been traveling for 4 hours. She's been traveling for 1 hour plus the 4 hours that he was traveling. And that would be the way that I would interpret this problem. So Nicole's distance is going to be 5r. And Jonathan's distance, or John's distance, is going to be 4 times r plus 12. So rate time of one equaling rate time of the other. And then I'm going to move down here below my chart and clean that up. So that gives me 5r, and that's going to be 4r plus 12 times 4 is 48. And therefore r is 48. And this is a, let's see, number 7 is a kilometer. Yeah, this is a kilometer per hour, kilometers per hour. 48 kilometers per hour would be Nicole's rate, and then his rate would be 60. He would be traveling at 60 kilometers per hour to add 48 and 12 together. Let's move on and look at number 10. So number 10, to get the words for number 10. All right, so I've got in number 10, I have an Air Force plane and a cargo plane. So the Air Force plane left Paris, flew east. 4 hours later, a cargo plane left flying 112 miles per hour faster. So in this particular problem, I'm going to let the Air Force plane be R. Cargo is R plus 112. 4 hours later implies that the other plane has already been in the air for 4 hours. So I'm going to let that be 4. And then as I continue reading the problem, after 6 hours, the cargo plane finally catches up to the plane that left first. So the cargo plane is flying for 6 hours, and the Air Force plane has been flying for 4 hours before the other plane departed, plus the 6 hours of the cargo plane. So this particular problem, setting these two phrases or two expressions equal to each other, 10R, and then solving my equation, and that's going to give me 10R, and then 112 times 6 is 672. And then the rate ends up being 168 miles per hour. And so the Air Force plane is 168 miles per hour, and then 168 plus 112. The cargo plane would be 280 miles per hour, and this would be 168 miles per hour. You could answer anything that's asked once you have that information. And I do want to do one more problem. I would like to do number 18 before I stop the video. So number 18 from the same problem set. And number 18, I have the two names in this particular problem set, Jacob and Wilbur. So I've got my chart labeled. J and W, rate and time, and as I read the problem, Jacob left school, traveled south at an average speed of 35 miles per hour, so I'm going to go ahead and fill in 35 in his rate column. Sometime later, so that really doesn't tell me much, sometime later, Wilbur left, traveling in the same direction, but his speed is 42, so I can go ahead and fill that part in the chart. And as I continue reading, Wilbur caught up with, let's see, after traveling for 5 hours, Wilbur catches up with Jacob. So I know that he's traveling for 5 hours. Jacob's been traveling for unknown time before Wilbur leaves, plus the 5 hours that Wilbur's been traveling. And then I set these two equal to each other, set these two expressions equal to each other. And I just wanted to make sure that you all had enough examples to work with. And that's going to give me 175 and 210. And that equals 35. So T is 1, which means that Jacob was traveling for 6 hours. So Jacob was traveling for 6 hours and his friend was traveling for 5 hours.